So feel free to ask me questions anytime. I really don't mind. So this is joint work with Sham, Pyotr, and Or, their respective affiliations. Okay, cool. Okay, so I'll begin. Oops. All right, so what is the motivation? It's like, a lot of algorithmic problems in high dimensions have runtime dependence on dimension. And it'd be nice if we can solve the problem that we want in a lower dimension, and that would speed things up, right? So here we have some points, and we want to just like project them into a smaller space. Okay, so this is like a lot of words, but sort of the main statement in this area is the so-called Johnson-Lindenstrass lemma. And all it says is if you have n points, you can project it into roughly log n dimensions that preserves all pairwise distances. Okay, so I just like rewrote it. We can preserve all distances. And this is very nice. It has a lot of like theoretical and practical benefits. And you can take, and this mapping is also really simple to do. Most of the time, you just use a random matrix and it'll work of the appropriate size of any like natural distribution that you want. Okay. All right. Next. Okay, cool. So the GL lemma is nice, but now the question is, can we do better than the GL lemma if we're only interested in specific problems? So the GL lemma has this like, very nice statement that all distances are preserved. Maybe we don't care about all distances being preserved. Maybe we only care about a specific problem. Can we do much better then? And there's a recent line of nice work by MMR19. We said if you care about this problem called k-means or k-median clustering, you actually can project to a much smaller dimension. You can project to only roughly log k dimensions. And what happens is that once you do the projection and you solve the clustering problem in that projected space, that clustering will actually be a good clustering in the original space that you care about. And just to remind everyone what this k-means or k-median problem is, it's just you have some points, you want to partition it into k parts, and the cost is measured by the distance from a point to its like center, associated center. So that's the cost, and you have k centers. Okay, so this is nice. So our main results is that we sort of study this type of problem for other clustering problems, in particular this thing called facility location and minimum spanning tree. Okay, so let me just define what these problems are. So facility location is like k-medians or k-means, except there's no fixed number of centers. You can sort of open however many centers you want, but you pay a cost for it. So here it's like you pay a unit cost to open, but it can be like 10 times this or whatever constant you want. So it's like a variable number of centers. And what is minimum spanning tree? Okay, hopefully everyone knows that, which is just you want to make a tree of your points, and the cost is measured by the cost of these edge lengths. And these are all like the distance costs Euclidean. And this minimum spanning tree relates to some other clustering problem called hierarchical clustering, but I'll mostly be talking about this minimum spanning tree. Okay, so these are the two problems that we're interested in. Any questions or confusion? Yes?
Sorry, you said that you could reduce it to dimension log n in approximately preserved distance. What is approximately preserved distance?
Right, so let me just go back to the statement. Yeah, so I have a trusty umbrella. Okay, it basically means that, this f of x will be represented in log n dimension, but if you measure their distance, it'll be like close to the actual distance up to some small multiplicative factor.
Okay.
Yeah, so it's like, all the distances are like basically the same, but their vectors are like much shorter. Yes?
What we're trying to preserve that the solution quality is similar to the original solution quality, or that the solution itself is similar to the solution you're trying to.
Yeah, so I'll talk a bit actually about that in a bit. But the idea is like, you want these things to be useful, right? So what you want is if you solve the clustering problem in the projected space, it's actually a good clustering in the original space. So we want to preserve like the quality of the solution in some sense. I'll talk a bit more about that actually. So, okay, so these are our two problems. All right, so so for the k-means problem, we had this natural parameter to sort of say what the projection depends on. But in facility location or minimum spanning tree, there's no K, right? There's no like number of centers or whatever. So our dimension results depend on this thing called doubling dimension. And it's, I'll talk a bit more about it, but it's sort of a measure of intrinsic dimensionality of the point set that you have. Okay, so let me define it first, right? So like I said, our projection bounds for these two clustering problems depend on this thing called doubling dimension. Okay, so let me define it. There's like a lot of words, but I'll talk to it. First, there's a thing called the doubling constant. And the doubling constant is basically the following. If we have a ball of radius r, how many balls of radius r/2 do we need to cover this ball? So in particular, the doubling constant is lambda if for every, for every ball of radius r around a point in your point set, we can cover it with lambda balls of half the radius. So, if you can imagine like in r to the m, if you have like infinite sets, right, the doubling constant is 2 to the m, right? So what is this doubling dimension? This doubling dimension is log of the doubling constant. Okay. All right. So this is like the main definition. If anyone has questions, I can. But it's just a measure of this intrinsic dimensionality, and I'm gonna refer to as dx. Yes.
Sorry. So to be clear, when you say cover, it's not cover the space.
Right. It's cover the points. Yeah. Exactly.
The worst case, so it needs to be true.
Yeah. It needs to be true for all radiuses. Yep. Yep. Okay. So the doubling. Right.
It would be at most one.
Yeah, exactly. Yeah. Yeah. And for finite point sets, this doubling dimension is at most log n, because you can just like put a ball around every point for every radius, right? So this log n is nice because it's like the JL parameter, right? But for a lot of point sets, even if n is really large, this doubling dimension can be much smaller, even constant for really large data sets. Okay. So all our projection bounds are sort of based on, yes, Samson?
So for these clustering problems, is the doubling dimension D or the K?
So the doubling dimension is a property of the point set, like regardless of what problem we care about. Yeah.
It's bounded by both log n and K, or sorry, log n and the input dimension.
Yeah, exactly. Yeah.
In practice, it's often like much smaller.
Yeah. So it can be much smaller. Yeah. So I think computing the doubling dimension exactly is hard, but I'll give some really nice examples of like large point sets that have small doubling dimension in a bit. Okay, yeah, and then factor 2 is good enough, I think, for balance. Okay, so before I talk more about results, there's two types of results, right? One is like, if we solve a clustering problem like k-means or facility location, it comes with a number, right? Like it says 10, which is the objective value. And there's another type of result we care about, which is the solution quality, which is if we solve a clustering problem in the project dimension, is it actually a good clustering in the original dimension? So both are important, but the solution one is like more important, right? The cost is just like a numerical value, like 105, whatever. But the solution is what we care about, right? If we actually want to do clustering. Okay, so there's two types of results. Okay, now I can talk more about our results. Okay, so for facility location, our results are the following. We can project to a dimension that depends on the doubling dimension of the point set. And if you solve the problem in the projected space, the cost of the numerical value will be preserved. And also any solution that's sort of like something called locally optimal, you can think of the optimal solution, will actually induce like a constant factor optimal solution in the original space. Okay. For minimum spanning, we have a slightly stronger guarantee, which is if you actually solve for the optimal minimum spanning tree in like this projected space, it's going to be at most 1 plus epsilon times worse than the actual optimum in the original space. And by this 1 plus epsilon, I mean in terms of cost. So this sort of says something which is what we want, right? Like if we solve the problem in the projected space, we're sort of given the guarantee that it's a good solution in the projected space, which is like the natural thing we want.
But it's a good guarantee in the original.
Yeah, exactly. Yeah, sorry. Yeah, that's what I meant. Yeah. Yes.
Are you saying a solution in the smaller space corresponds to a locally optimal solution, or approximately locally optimal solution?
Yeah, so right, so I haven't defined what this is, but you can think if I solve for the optimal, or if I solve for a constant factor optimal solution in the projected space, it'll actually be a constant factor optimal solution in the original space with respect to the actual optimum.
Okay, and that's in a global sense now.
Yeah. Okay. So these are our results. And so these bounds are tight in various ways. Obviously, like there's some ways in which they're not tight, and I'll talk about it at the end. Okay, so let me I'm not gonna go over the proof, but let me just give you like the high level flavor of like how we prove these things. The cool thing that I liked about this problem was that you actually had to use properties of the clustering problem. It wasn't like an oblivious analysis that you use for JL, for instance. Okay, so in the left-hand side, I just rewrote what facility location is. Okay, so first let me give you one property of facility location that we exploit in our analysis. So it turns out that for every point in our data set or point set, you can associate a radius to it, which I call R sub x. And the radius is defined as follows. I just keep expanding a ball of radius of this for some radius until this dotted lines add to 1. Okay, so there's some number, right? We don't know what it is, but it's like some number. So for every point, I can associate a radius to it. Okay, so yeah, awesome.
Yeah, I didn't quite understand what the bottom was.
It's just like if I have a ball of radius r, right? Then I know some points of my data set or point set will be included in the ball, so that I can measure this distance, right? Which is like this distance minus this distance. Yeah. Yes.
Is the dotted line like 1, 0?
Yeah. So we don't care about the points that are not in the ball. Yeah.
So if I have no nearby points, I'd be like 1.
Yeah. Exactly.
And if I have like 10 nearby points,
Like 1 over n. Yeah. Exactly. Yep.
Sorry, maybe I missed it, but what is your dimension reduction?
Oh yeah. So it's just the standard Gaussian matrix for JL. Yep. Yeah. But just the analysis is non-oblivious. Okay. All right. So so far I'm just talking about facility location, not about dimensionality reduction or anything. Okay. So for every point, we can define this radius or associate a radius to it. And it turns out that this radius has some nice properties, which is the cost of the optimal solution can be parameterized in terms of the sum of the radii. And also, it turns out that every point needs to have a facility, maybe not exactly, this may be like 3 times the radius or something. And the reason is if there wasn't, then you could just put a facility there in the ball and it would like reduce the cost. And that kind of makes sense, right? If too many points are not being served, we can just serve all of them. Okay.
To be clear, 1 is the cost of an additional facility.
Yeah.
So if facilities have the cost, this would just be the ball equals the cost of the facility.
Yeah, exactly. Yeah, so the idea, or like you said, if there's too many points in a ball, we can just serve all of them. They will pay only this radius cost, and that can be that's not as much as the cost of opening. So the overall cost goes down. Right. Okay, so now let's tie this back into like projections. So it turns out that the main step in this facility location analysis is the following lemma that we want to prove, which is consider what happens in the projected space. If there's I'm gonna use my trusty pointer. Okay, so let's fix a point. Okay, pi denotes projection, and this f is a random point. So if we pick a facility in the projected space that's close to x, and by close we mean close within this radius, but now this radius is calculated in the projected dimension, then actually the expected distance in the actual space is roughly equal to the radius in the actual space. This turns out to be the key lemma. And why is this important, or why is this, why do you want to prove something like this? It's basically because, right, all the costs in the projected space are like roughly in terms of the radii, right? Because that's what I described before. The radii sort of control this facility location problem. So you want to say, if I pick a facility for a fixed point, within its ball, then it's actually like not that bad of a point to pick in the actual space. So if I prove something like this, then it's like a major step in proving that the solution found in the projected space is a good solution in the actual space. Okay. This is, yes. Pi x is this, so we're projecting the points, right? So pi x is like the projected point. So it's like pi is like a matrix, I guess. Yeah. Yeah. So just the point in the projected world, I guess. Yeah. All right. Yeah, in points in x. Yeah. Yeah, points in x. Okay. So this is the major step. Okay. So before I talk about proving it, I'm not going to prove it, I'll just give high level ideas. There's something interesting happens with random projection, which is that so pi again is denotes projection. The probability of distances expanding by some factor is really small. So if we project to, like, let's say dimension dx, or it doesn't have to be dx, or whatever, the probability of expansion is small, but it turns out the probability of shrinking is actually much larger than the probability of expanding. So there is an asymmetry here at play. So this is like a cool fact. Like expansion has much smaller probability than distances shrinking. Okay, so now let's go back to what we want to show, right? We kind of want to show something like this. X, here's a fixed point here. If I pick a point pi of p in the projected space that's close to x in terms of this radius, actually be not too far away in the original space. Okay, that's kind of what I want to show. Okay, so let's just go through the steps and I'll show you where the doubling dimension assumption really helps. Okay, so first, right, we want to control this expectation, which is the distance to my facility, let's say, in the real space. Well, okay, let me just introduce some events. I haven't done anything. So first, I'm going to take my point x that I'm interested in. I'm going to consider sort of layers around this point, and each layer is sort of going to be linearly increasing based on. So I'm dropping the x notation r of x, but everything is in terms of this fixed point x. So I'm gonna have layers around my point, and I'm gonna say, okay, let's just add events that correspond to each layer. So I haven't done anything. Okay, so now I'm gonna introduce more complications for no good reason, but we'll see later. Which is, so if I let E sub I be the event that my point P that I picked in the projected space is in the ith layer, right? So then I can write the expectation as this conditional expectation. Now let me introduce more events. So the event I want to introduce is, I want to introduce how does my radius change in the projected space. So I want to say, well, I can just introduce these events, which is the event that the radius is in some range. And this range is right, there's a new index. This range is independent of I, right? So so far I haven't done anything. I'm just introducing a bunch of events. Yes?
Sorry, so P and X are specific points in the original space.
No, so X is fixed, but P is a random point, right? P is a point that we pick to be X's facility.
Okay, but P is, so is the expectation over P when you take that expectation?
The expectation is over this like randomness of the projection.
Okay, so the set of P that are eligible depends on the randomness of the projection.
Right, yeah.
But like, I guess, so this is saying for each P, we look at the probability that it's eligible under the random projection. And then these events.
Yeah, kind of, yeah. Yeah.
But the ith layer is defined prior to the projection.
Right, so the ith layer is, yeah, that's why we have this,
So
we have this probability, right? That's why.
maybe I'm not understanding something, but I don't understand why, whether P is in the ith layer has any randomness involved. Because that radius is defined in the original problem, which has no randomness.
Right, so I guess what could have happened was that the facility that you picked in the projected space for our fixed point X could have come from really far away, right? And that's kind of what we want to capture. So we can say, okay, what if it came from this distance? What if it came from the next distance, and so on.
The way I was reading it is that P is the, you project it down, and then P is the facility you fix downstairs.
Yeah.
Oh, then this is you unprojected it.
And then you
Yeah.
project. Exactly.
Right.
The 5P is the one that you fix down.
Yeah, exactly. Yeah, exactly. Sorry.
The P is this random object.
Yeah, P is a random object that we hope to control. We want to say P could not have been far away in the actual space.
What we're really saying is for a given lower space,
Right.
what's the chance that in the unprojected
Yeah.
space things have good properties?
Yeah, yeah,
Oh,
Yeah.
100%.
yeah. Right. So I'm going to introduce a bunch of seemingly useless events, which is first I'm going to say, okay, what is, I'm going to decompose my distances from X into different layers. And I'm going to say, okay, suppose P came from this layer versus that layer and so on. That's what probability of EI is. And then now I'm going to introduce the events that the radius of X, so there's an X here that I'm ignoring, radius of X changed under the projection, okay? So far I haven't done anything, but now let's see where things come in, right? So like I said, if I condition on something, then I know what this value is at most I times R, because I'm supposing it's in some layer. So I just need to bound this probability. Okay. All right. So let's see how this works. So first, right? What is this thing, right? This thing says the radius of. Oh, okay. All right. This thing says the radius of X. So if J is big enough, this thing is saying the radius of X, right? Because Tj is like J times R. The radius of X increased a lot. So what does that mean that radius of X has increased a lot? It means the ball around X significantly expanded, right? Because if it hadn't expanded, the radius would have been small. Because the points that are in my ball must have gone farther away, right? So if I pick J to be large enough, right, then this expansion probability is really small. So that helps in this sum, right? So like, what's my goal, right? My overall goal is I want to bound this probability. So I'm gonna first look at this particular term first for J large enough, right? And this is saying if the radius expanded, well, like I said before, right, the probability of expansion is really small. Distance is expanding. So that's going to be helpful here. I'm just going to plug that bound in here. And this covers some range of J. So this range is fine. And now for the other range of J, I'm going to ignore this formulation. I'm going to go back to this formulation, right? So what is this saying, right? This is saying that my point P was in this ith layer, but now it came all the way back to be in my radius, right? So what does that mean? That actually implies that this faraway point shrunk a lot to be close to my point, right? Because we're sort of assuming that this pi of P was within radius R of pi, right? Because that's why we picked it. So like, this is saying point P is in the ith layer and the radius is not that big. But if the radius is not that big and the point P was in the ith layer, it must have shrunk a lot. And even though I said the probability of shrinking is not that powerful, here if I make J like much smaller than I, it turns out that this shrinking is so much that it's powerful enough. And this is where this doubling dimension really kicks in, because I need to sort of union bound over all the points in this layer. But because of this doubling dimension hypothesis, I can cover the layer with few representatives, right? That's what the doubling dimension gives me. It allows me to cover every layer with few representative points and just argue for that. And that with the shrinking bound is strong enough for the other ranges of J I care about. Yes.
Don't I expect J to be like close to R? Like, the distances of, in order space and distance in projected space should be about the same. So J and I should be of the same magnitude.
Right. So
I'm wondering why the probability of J, because the square root I is going to be tiny. I would have expected it to be much bigger than J, much bigger than I.
Right. So I guess that's kind of why we introduced this parameter, this other like event. Just yeah, like you said, yeah, like you said, you do expect these distances to be roughly the same, but I guess because we're projecting to some dimension that we don't even know, like there's still some chances of things being really distorted. So I guess we just have to think about, we just have to cover our bases, I guess. Yeah.
So in the projected world,
Right.
it's very close. It's in layer 1.
Yeah, exactly.
And then the unprojected world is very far. It's in layer I.
Right.
So we sort of have these two weird things happening at the same time.
Right.
And we're saying, okay, if J is high, it's weird for one reason. If J is low, it's
Yeah, exactly. Yeah, it's just maybe you should speak.
So you're saying that, look, everything else being the same, P is in layer.
Yeah.
That's really good.
Yeah.
That's really driving that second term.
Yeah.
The expression that you had in the previous slide. That's really driving.
Right. Yeah. Right. So just to pick up my thoughts where I left them up, this part is where the double dimension thing comes in, because right, we're sort of, we need to argue for a layer, but a layer can have like, ton of points, but we can cover the layer with small number of representatives. That's what the doubling dimension things lets you do. Okay. All right, so that's all I'm going to talk about facility location, just to give a high level idea. We just had to balance the shrinking and expanding in some nice way to get things to work. And this like radius property really helped us out. Okay. Let me like briefly talk about minimum spanning tree. Okay, so on the left side, I wrote the definition of minimum spanning tree, right? We want to minimize the sum of the edges that makes a tree. Okay, so the proof strategy is very different. So let me just like assume that all the distances in the original space are roughly equal to one value. This is not going to be true, but for the sake of this argument, let's just say that. Then I can partition my space into small number of balls because of this doubling dimension hypothesis, right? Of radius like something small compared to t. Then I know the following, right? I know that these balls are not going to expand. That's what I've been talking about. Balls don't expand, but some of them might come really close to each other, and that's bad. But it turns out minimum spanning tree has this nice property that, okay, if a pair of faraway balls comes together in the projected space and we like join an edge between them, right? Then in the original space, these edges can expand, and that's really bad, right? The minimum spanning tree just like blows up. But it turns out that each bad pair can only contribute one bad edge. Why? Because in the projected space, right? If you were like connecting two balls like this, then you would have just like done this instead or something, and still maintain the MST property. So what ends up happening is that even though, faraway balls can come close to each other, they have sort of a controlled amount of damage because they can only contribute like one bad edge. Yes, or I can.
Sorry, how can a ball have more than one vertex in it? If all the distances are around t and the balls are very small compared to t?
Yeah, so this was like a very high level sketch, but yeah, so let's just assume, these balls have more than 1 points.
Oh, we're choosing C, so they have a few points.
Yeah. I guess the key idea that I wanted to get across was that things that are far away coming together can only have a bounded amount of bad impact, because in the actual MST, like we never pick like too many edges across different balls, because you can just like pick one edge instead. And if they only have 1 point, then you already have only one edge anyways. So anyways, I think the question.
So
Yeah.
it's a question about the previous one.
This one or?
So here, even if you are able to cover the points they have small text by doing the doubling dimension, that accounts for the probability that it's to be small. Don't you feel like a distance r where you sort of each one, like if you use the proxy at the center?
Right. So what you end up doing is you cover this layer with small number of balls. The balls themselves don't expand, and that's And then so you can just think about the representative of each ball. And if you control what the representative does, then you know what the ball does because you know the ball didn't expand.
But then aren't you like just kicking the can down the road? I mean, like you're saying like from the center of the ball to every point of the ball, you have to preserve these distances. Or like
Right.
argue that they don't shrink and expand.
Right. So we only care about them expanding too much. And for expanding, there's like such strong probability that it doesn't end up hurting you. It's just that these layers, like shrinking is like the where you don't have enough probability.
Yeah, if you care about the points in the ball shrinking as well, that's argument more for it.
Yeah, yeah. Right. Yeah. Yeah. Okay. So this was like a more informal proof than the last time. But here I just wanted to highlight again that like we're really using the fact that it was an MST that like lets us do this like switching thing. Okay, let's see. Yeah, and then this like switching thing was a key idea, I guess. All right, so we had some experimental results if you're also interested. So we just took some like data set and then maybe I'll explain this graph. This was for a minimum spanning tree. This blue line, sorry, this orange line is saying how much it costs to in runtime, like to compute the MST in various projected dimensions. And this blue curve is saying if you take the computed MST and like evaluate against the actual MST, it's gonna be worse, but like by what factor is it worse? So even though the dimension of this point set originally was like 4096, you could just project to like 20 dimension and only get like 10% worse MST. And then it gave you like 2 orders of magnitude speed up, which was nice. Okay, so one thing that I thought of when I saw this was like, okay, maybe this is just because of JL. Like, how do we know this doubling dimension is actually helping us? Like, maybe it's just like an artifact of analysis or something. So then we created like 2 point sets that are very similar, but they have very, very different doubling dimension. So the first point set is just like basis vectors, E1, E2, and so on, but we like add them together, like E1 and then E1 plus E2 and then E1 plus E2 plus E3 and so on. And the second point set is like the same thing, except we don't add them together. We just keep them separated. Okay. So it turns out that this first point set has one doubling dimension, no matter what n is. But the second point set has like log n doubling dimension. And sort of the reason is that these points are like spread apart. So you'll need like, you just think about the definition of doubling dimension, it kind of becomes clear. While the first set of points are like kind of sort of in a snake pattern. So they're like kind of together in some ways. But yeah, it's kind of interesting that they have very different doubling dimensions. So it can be any number. So here we pick like random Gaussians just to throw some randomness. But for the sake of thinking, like you can just ignore these GIs. You can just think of 1 and E1 plus E2 and so on. Okay, so then we computed this like MST, and then we pulled it back and we saw, so like we computed the MST in the projected dimension and then evaluated its cost in the actual dimension. And you can see that this low doubling dimension point set needs much fewer dimension to get like within 5% error than this high doubling dimension point set, even though, conceptually they're like very similar. So that was kind of cool.
So you would need the Gaussian, you would need the GI, because otherwise
right. Yeah, exactly. That's why to make it asymmetric, we did that. Yeah. Yep. Okay, so like I said, similar points, but very different projection behavior. And so the doubling dimension is like important, I guess. Okay, so open problems. So the two most clear ones are okay. For first location, we only have this constant factor type bound. So it would be interesting to get 1 plus epsilon. This MST had an extra plus log n term. It'd be interesting to get rid of it. But I think the more interesting open problems are like, what about other geometric problems? So like, what about other problems where we find JL could be possible? So, you can think about traveling salesman, matching. I think matching is the cooler problem. We have like some partial results for matching, which says, you really need log n projection dimension. But it turns out the bad example we have has doubling dimension log n. So in some sense, JL is tight, but it could be possible that you could get a better dependence if you parameterize it in doubling dimension. And matching is something that actually people compute a lot. Like in machine learning, it's called optimal transport, which is fancy, but it's just matching. So yeah, if you could prove something, that would be really nice. Okay, I think that's the end of my slides. If anyone has any questions. Thanks. Okay, I think so. I actually know the TSP answer, which is you can get the same for minimum spanning tree. You can do 1 plus epsilon. Like you can project to doubling dimension plus log n over epsilon squared, I guess, and then the TSP you find will be at most 1 plus epsilon worse than the actual TSP. And the reasoning for that is MST and TSP are like very related, right? There's like a right, a factor of 2, but the idea that, right, it turns out for matching, the idea that you can switch things actually turns out to be true for MST. Oh, sorry, for TSP.
The idea being you don't want to have more than a constant number of edges out of a small group.
Yeah, exactly. Yeah, which turns out for TSP, right? If you had a bunch of edges going back and forth, we can just like go this way and go this way and make the TSP a little bit better. So it turns out the answer for TSP is this at least as good as the MSC answer, but this matching I have no idea about. Yeah, I think vanilla matching is also interesting. Vanilla matching does have this bounded error type property, right? Because if you're like, okay, let me go back. Go back to this, right? If you're matching many points here across, you can just like match them this way. So it has some of these nice properties, but it doesn't quite work, I think. So yeah, that could be a good first step, I think. But this red blue is more, at least what I'm personally interested in.
Can you go back to the facility location slide?
This one?
No. Well, yeah, what it's still confusing to me what the want exactly is taking the expectation over.
Yeah, so the expectation is over the randomness of the projection. It's like saying I do a random projection and I find a facility near my fixed point. Okay, how bad is it in reality? If I know that I didn't pick it to be too far away in the projected space.
So the expectation is over projection. You find some point which is close in.
Yeah, exactly.
The projection part B.
Yeah,
You
exactly.
make the pre-image of that.
Yeah, exactly. Yeah, yeah. So it's kind of a little wonky to think about, but yeah, it took me a while to think about it, like understand it fully. Yes.
Yeah, maybe the bracket should be over the entire thing, and expectation should be out or something.
Okay. Yeah, that's true. Yes.
So to sort of summarize what the key properties you need in each case. So I think you did a good job summarizing the MC case, but I'm not super clear what the properties of facility location.
Yeah. So facility location, like the key thing was like we were analyzing these radii. They served as a proxy for the cost and like how good the solution was. So we just need to understand like if I picked a point in the appropriate radii in the projected space, it's like it'd be a good radii away, or like its distance won't be too bad in the real space. So yeah, I guess the idea here was like we really use this like radii thing a lot, which is something about the problem, which is cool.
Yeah, but it doesn't seem like this way of thinking would lead to a 1% of appropriation.
Yeah. So yeah, I don't think it will. But also like facility location is an NP hard problem. So in some sense, it's like okay, maybe this is fine. Yeah.
Okay, so we're sort of saying if solution quality only depends on like local stuff not getting much further away.
Right.
Doesn't really care if local stuff gets closer because this is making the solution even better.
Yeah. Yeah. So for these, like at least for matching, I fully expect if it's solvable, it will use like some property that matching has in some way. I don't know though. Yes.
Go back to like the slide.
Oh, this slide.
Yeah. Wait, so is it actually the case so like for like all I that's like I guess larger because like probability of E1 is not the case. It's one.
Yeah, so the probability of E1 is not small, but then like these first few EIs just give you like R, right? All of R. Yeah, exactly. That's why this, so this, there's a constant factor of blow up.
For large I, you sort of over like this J that you define. Is it actually the case of like thinking of this in terms of like two distances shrinking, like gives you like J less than equal to I small?
Wait, sorry.
Like you like analyze this in terms of like 2 points, one of
Yeah.
those are like all the spending.
Right.
Like the probability of the other one's like distance in connection.
Right.
Like is it actually the case of like these two like was one regime like basically like one settles the case like J is greater than this for I and settles the case of
Yeah, maybe there's a better way to do it if they overlap, like better analysis, but I don't think it would give you a better result. Like you still get this constant factor blow up, right? Like you can't really hope to say anything for E1, right? Like E1 is like, it's not shrinking or expanding because it's like so close, or E2 and so on. You can only hope to say things for like large I's anyways. Yes.
So the projection matrix uses like the standard gas also.
Yeah.
Is it possible to put stars into
Yeah, I think if you use like plus or minus one random matrices, or this thing where you like 1/6 of the time is 0, and then the next, or like 1/6 of the time is plus or minus 1, 5/6 of the time is 0, that would work. I don't think any of these fast transforms where you use like the Fourier matrix works. Yeah, so some sparse matrices would work, but probably not the best that you can do for regular GL.